Hi, welcome to the first video on the topic of mapping entity relationship designs onto relational database schemas. And this relational database schemas, of course, will be expressed in the SQL data definition language. So I thought I'd start off with a fairly simple example, two entities and their corresponding attributes, both of which don't have many attributes, and there's no relationships at all in this system. So we're just going to focus on how we map entity attribute descriptions into relational tables. Okay, well, let's start with the staff one. Generally, an entity in an ER diagram will map to a relational table, and so it would make sense to call the first table staff. So we've mapped the entity, if you like. Now you can see that the entity has three attributes. It's got staff ID, name, and subjects. Now, of course, anyone who was paying attention in the lectures would realize that subject is a multi-valued attribute. And that means essentially that you can't have a single value, you can't have a single attribute with a single value for that particular attribute in the staff table. So the way we map multi-valued attributes is we actually take them out into a separate table. And each entry in the table represents the fact that a particular staff member can teach a particular subject. I guess I should have said that initially, so that the subject's multi-valued attribute represents the fact that, say for example, Mr. Smith teaches maths and Mr. Smith can teach physics. You might also have that Ms. Jones teaches English and Ms. Jones also teaches geography. So what we have to have in this table is essentially like a relationship between the staff and the subject, except subjects aren't a separate entity in their own right. So all we're doing is setting up a link, or allowing for a number of possible subjects to be associated with each staff member. So we have to say who the staff member is, and we have to say what the subject is that they teach, and I'll talk about the primary key for that in a moment. So you can see that I've partially filled these things out. So once you've decided what are the entities and what are the attributes of your tables, you've then got to decide what types they have. That's one nice thing about ER designs. You don't have to worry about, fiddly details like data types. In any case, so staff ID, generally for an ID type value we do an integer, so an integer value. Now staff ID, obviously, certainly because it's underlined in the ER diagram, and also because I've been kind of hinting that it's a unique identifier, is going to be the primary key for this table. Okay, so we've got the staff member's name. What data type should we do with that? Well, generally we'll have some kind of varchar value. That at least is standard. I'll stick to that in these examples. So let's say no staff member's name is longer than 50 characters, but of course some might be shorter than 50 characters. So that would capture the information about the staff member's name. Not quite, perhaps. We don't want to have staff members who don't have a name, and so we might want to specify an additional constraint that the staff member's name is not null. Now you might say, why don't we do the same for the staff ID, because we don't want someone to exist as a staff without an ID, and well, that's pretty straightforward. The fact that it's a primary key in SQL implies that it can't be null. So that's implicit. If I really wanted to, I could certainly put not null there, but it's redundant because staff ID is the primary key, so I won't do that. Okay, so staff ID here is going to be an integer because it's a foreign key that references the staff ID field. Okay, so staff ID is an integer containing a value that will appear as a staff ID somewhere in the staff table. Technically, we might want to be a little bit careful here, and we might want to insist that it's not null. The fact that it's a foreign key doesn't prevent it from being null, and so I could add that additional constraint. Now you can see that it's overflowed the line. If you find that a problem, there's an alternative way of specifying foreign keys. Oops, didn't want to do that. What I can say is that a foreign key staff ID is, or a foreign key staff ID references the staff ID field in the staff table. And generally I'd put all the keys at the end. And I think in SQL I need parentheses there as well. Okay, subject. What kind of data type can subject will be? Well, subject is just the name of a subject. Once again, we could do a varchar, maybe just to throw in a little bit of PostgreSQL specific syntax. Postgres has a string data type text, which allows you to have arbitrary sized text fields. So rather than having to decide, well, no subject has a name that's longer than 100 characters, you can just say text and not worry about that. I could have done the same thing for the staff name. Now I defined staff ID to be not null. However, it turned out that was actually redundant, because what's the primary key for this table? In fact, the primary key is the combination of the two attributes in the table. And one way you can reason that is that it doesn't really make sense to say Mr. Jones teaches maths and then in a different tuple say Mr. Jones teaches maths. Once you've said that, you've already made the point. So you only need one instance of a particular staff ID subject combination. So having said that, that would actually remove the need for the not null constraint up here, because as I said before, anything that's part of a primary key is implicitly null. So that's how we've handled staff. All right, so now let's take a look at student. Student's got a few more attributes and there's a few more different data types, but by the same kind of reasoning as we had before, we'll probably create a table for the student entity. Since we're going to have lots of students, I'll call it students rather than just student. And now we start filling in the attributes. You can see it's got a student ID, and there's a fair bet that's going to be an integer and it's going to be the primary key. Okay, we want something that uniquely identifies the student. Alright, what other fields have we got? Well, here we've got a name again. We could either use varchar 50 and be standard, or we could be lazy PostgreSQL programmers and use the text type. Now once again, we don't want a student who doesn't have a name, so we might want to make that not null. Now it's perfectly possible, if you want to form roles that are in alphabetical name of the student's family name, you might actually want to split the name into given name and family name. But let's say for the sake of argument, we'll keep it simple here. Alright, the birthday type is clearly going to be a date. Now maybe we don't care if we don't know a student's birthday. Maybe that's not particularly relevant, so we won't bother declaring that to be not null. So we can have students in the database whose birthday is not known. Potentially you could have some kind of constraint on that. You don't want students who were born in 1700, but then if this database was to persist for a long time, maybe we do want to have students with birthdays a long time in the past. Now the year attribute here, this is a nice example. It's not the student's birthday year. It's actually the year in school they are, year 1, year 2, year 3 up to year 12, say. So knowing the precise semantics of attributes allows you to specify more precise data types. So here we're not talking about a date, we're actually talking about an integer, but it's not an arbitrary integer. You don't have year minus 3. So what we could say is that the year has to be between 1 and 12. So we've added a check constraint. So any tuple that has a year value, and notice we haven't declared it as not null, so potentially we may not know what year they are. But if we know what year it is, it has to be one of the numbers in the range 1 to 12. Alright, now I was just about to put hobbies, but we can see that hobbies is a multi-valued attribute, so we have to use the same strategy as we used above. So we'd have a table that connects up students and their hobbies, connects them up one at a time, if you like. So here I'll be a little bit different. I could call it StuID. It's not essential that it has the same name. Potentially I could call it student, and that will be an integer, matching the fact that it corresponds to the student ID. And the hobby, once again, it's just going to be the name of the hobby, playing cards, collecting stamps, reading books, something like that. So that's going to be an arbitrary text string, so we'll just define it like that. And the reason we don't need to say not null is that these things are going to be part of the primary key. So this combination of student and hobby has to be unique in the student hobbies table. Now the other thing I haven't done yet is I haven't specified that student is a foreign key, and I could do that like this. By saying that student is an integer that references the StuID field in the students table. So here I've explicitly said it's a foreign key. Here I don't need to say that if I do the references inline, if you like. And I think that's completely covered that particular pair of entities. So hopefully you learned something useful from that. Mapping entities, generally each entity is a table, and the thing you have to do with the attributes is decide on the data types. To be precise about that, you need to understand the precise semantics of the problem. Okay, that'll do for this time.